Now let's look at the left-hand side of Stokes' theorem for this example. In the previous video, we found out that the integral on the right side was negative 6 pi, so we hope to get exactly the same answer here. Remember that the boundary of the surface S is made up of two curves, C1 and C2. C1 is this circle down in the xy plane, which we found in the previous video to have a radius of 2. And C2 is the curve in the plane z equals 1. And we found that that curve had a radius of 1. So the integral around C of f dot over ds will be the integral along C1 plus the integral along C2 of f dot ds. So let's parameterize each of the curves separately, calculate the integrals, and then add them together. Let's begin with C1. C1 is a circle in the xy plane. So when I'm parameterizing, I know that the z coordinate is 0. It's in the xy plane. And a great way of parameterizing a circle is r cosine t, r sine t. But we know that r equals 2. So I can do 2 cosine t, 2 sine t. Or writing this in sigma notation, I'll have sigma 1 of t equals 2 cosine t, 2 sine t, and 0. Important to notice here, since I'm parameterizing a curve, there's only one parameter. You don't have to use the letter t, but no matter how you parameterize, there should only be one parameter. Now remember when we parameterize using cosine and then sine, that goes counterclockwise, and a counterclockwise orientation around the z-axis is exactly what we want. So we want t to go from 0 to 2 pi. That'll give us the correct orientation. So now that we've parameterized, let's calculate little ds. Since this little vector ds, that's simply sigma prime of t dt. Taking the derivative, we'll have negative 2 sine t, 2 cosine t, and 0 dt. So that's my formula for sigma prime, or for ds. So now let's figure out what the integral along C1 of f dotted with ds is going to be. Remember the vector field we're using is y, negative x, and z. In our parameterization, y is 2 sine t. Negative x will be negative 2 cosine t. And z is equal to 0. And I dot that with this formula I just found for ds, which is negative 2 sine t, 2 cosine t, and 0 dt. So important to remember, the x, y, and z come from the original parameterization. ds we calculated separately. Oh, and we know that t goes from 0 to 2 pi. Now let's carry out the dot product and then integrate. 2 sine t times negative 2 sine t is negative 4 sine squared t. Negative 2 cosine t times positive 2 cosine t is negative 4 cosine squared t. And then 0 times 0 is 0. Negative 4 sine squared t minus 4 cosine squared t is just negative 4. And then the integral of negative 4 d theta will be negative 4 theta, taken from 0 to 2 pi, is negative 8 pi. So the integral along C1 is negative 8 pi. Let me capture that there. And we'll continue to the curve C2. Now remember in C2, the z component is 1. This is up in the plane z equals 1. And this circle has radius 1. So our parameterization will be 1 cosine t and 1 sine t. So sigma 2 of t is cosine t, sine t, and 1. Now this one we want to have a clockwise orientation rather than counterclockwise. So here I'd better go from 2 pi to 0 rather than the other way around. Little vector ds is sigma prime of t dt, which will be negative sine t, cosine t, and 0 dt. And then we're ready to substitute in. The integral along C2 of f dotted with ds is the integral along C2 of y, negative x, and z dotted with ds, which will be the integral from 2 pi to 0 of, let's substitute in for x, y, and z. Y is the same as sine t. Negative x will be negative cosine t. And z is equal to 1. And that gets dotted by negative sine t, cosine t, and 0 dt. Now it feels weird to be integrating from 2 pi to 0, so let me swap that and make it from 0 to 2 pi. But I'll put a minus sign in front. And let's dot together the two vectors. Sine t times negative sine t is negative sine squared t. Minus cosine t times cosine t is minus cosine squared t. And 1 times 0 is 0. Now here, if I want, I can distribute the minus sign into the integral. So that inside I have sine squared t plus cosine squared t, which is 1. And the integral from 0 to 2 pi of 1 dt will be t taken from 0 to 2 pi, which is 2 pi. So just to write this a little bit more formally, the integral along C of f dotted with ds is the integral along C1 of f dotted with ds plus the integral along C2 of f dotted with ds. And from the calculations we just did, we found that that's negative 8 pi plus 2 pi, or negative 6 pi, which is the same thing we got on the right-hand side, and that's what Stokes' theorem guarantees will happen every time.